Yeah, so I'm going to talk about zkVMs, and I'll give a bit of introduction to these concepts since there's a lot of teams and projects that are building zkVMs and working with IVC and so forth. The problem I'm going to talk about is in zkVMs, if you use incrementally verifiable computation, you slice the computation in multiple parts. Those parts may be computed by different provers. And then the question is, how do you check that they have a consistent memory throughout that computation, right? Because there might be a write in one place and a read in a completely different place of that one. And it's a topic I've talked about before, but there's a new twist. We've been exploring this concept of multiset hashing and how efficient one can prove multiset hashing. And it's one of the techniques that one can use to do memory checking. There we go. Okay, so it's something that people have worked on before. There's a standard techniques based on Merkle trees, which is not very efficient. But then there are also some efficient techniques. The multiset hashing technique was actually came out in a paper in 2018 by Sentinel called SPICE. And then there are other techniques to pass offline memory checking, which is quite recent. And if you want to know about that one, you can check out my talk on ZK proof, which was talking about that topic. And there's also a nice idea by Bunce and Chen in the paper Proofs for Deep Thought, where they're doing a Peterson commitment to the full memory and then just making an update of a delta, the changes of the memory in each step at a low cost. Okay, so I'll start by giving some background to zkVMs and the problem that we are looking at in memory checking. So let's start without the ZK. So a virtual machine is a machine that can take as input a program, an explicit input X, and another input W, and then it outputs some result. And the question we are asking ourselves when we're building zkVMs is, how do we know that this output Y is actually true? So the idea in a zkVM is that you would also output a proof that this has been computed correctly. And then there will be a matching verification algorithm that can take as input the program and the input X and the output Y and prove and check whether this is correct or not. And it's important actually here that then the reason I split the input in two parts, right? So the W input is not part of what the verifier sees. And that's part of why you can have succinct proofs that are much shorter than the computation, that you don't actually give that to the verifier, and therefore the verifier doesn't have to read it, and the computation the verifier invests doesn't have to depend on the size of W. So this means that we can have proofs that are succinct, that are really small, really cheap to verify, and cheap in the sense that the verifier has to look at the program and the explicit input and the output and the proof, but not W. Okay, if we peek inside the zkVM, typical design is that you would have the virtual machine that produces an execution trace of every step that it executes and produces the output. And then you have a prover that looks at that execution trace and then proves that there exists a valid execution trace. So every step in the execution trace corresponds to a correct execution of an instruction. And those execution traces may be big, right? And computing proofs is an expensive operation. So one strategy could be that you would want to slice that up and you would have multiple provers. You would have many machines that are proving that this execution trace is correct. Okay, so let me dig into a little more technically speaking what happens here. So this is incrementally verifiable computation, a concept that was proposed in 2008. So think of this function VM as a state transition machine. It's all like takes what is the current state, it produces a batch of cycles, and it outputs so like what is the next state of the machine. And you can sort of do that in a sequence, and there may be some auxiliary inputs as well, right? And at the end, you would output Y, okay? And there's sort of like a lot of details into how you actually prepare that, right? So for instance, maybe it's a big program and big input X, right? And you wouldn't want to give everything in one go, so maybe you instead you have some sort of like digest of that, and then you're not actually giving, so like keeping that as state, but you're instead so like inputting that along the way as part of the auxiliary inputs, omega 0, omega 1, and so forth. So you can, for the purposes of this talk, think of the omegas as sort of like this is the execution trace that we're drip feeding into the zkVM. And then you would have a prover that sort of like proves that the first iteration has been computed correctly. And the next prover would sort of like consume the proof from the first prover, and so like the next slice of the execution trace prove that is correct, and so forth, right? And that way you accumulate these kind of proofs, and you get a proof in the end that everything is correct. So let's look inside now. What is it that this machine does, right? So think of this as we have a virtual machine. It has a CPU, and it has a random access memory. And one way we could think of this, so like the naive approach, and what people were doing in the early days when they were looking into zero-knowledge proofs for execution of programs, is that you have the state is everything that you have in the virtual machine. So it would have like a snapshot of what are the register values of the CPU and so forth. It would have like the memory and so forth, right? And then you execute it, and it outputs the new memory and the new state of the CPU. Now this is super expensive though, right? Because now you actually have to keep track of the full memory in each of these transitions, right? And who knows how many cycles, maybe you're executing a few cycles, and then it's really costly, proportionally speaking, to keep track of the full memory, right? And you have to place constraints when you're proving that this is a correct transition that constrains all of the memory, right? And a lot of the memory cells will just be unchanged, but you have to say this one is equal to what it was before, this one is equal to what it was before, and so forth. So the natural idea now is, okay, let's try to externalize the memory. So the state now will just be the state of the CPU, what are the register values and things like that, and where is the program counter at. But now we give the memory accesses as external input. So it would say, look, I was writing this value to address 3. I was reading this value from address 17, and so forth. Okay, and this reduces the cost for the prover, right? Because now we just have to keep so like the relatively small state of the CPU, so like what are the registers values and things, where's the program counter at, okay? But everything else has been externalized, okay? So you only pay for what you use, right? So you still have to prove something about the memory accesses you do make, but you don't have to prove something about the rest of the memory. Okay, so let's be naive and go with that straight away, right? What happens? Okay, so now the initial state is just the CPU state, and that's what we are progressing. And now we've externalized the memory accesses, so the memory would be, so memory 0 would be a batch of memory accesses, some reads and some writes. Memory 1 would be some accesses again to the memory and so forth. And we're basically giving that as advice to the CPU. Okay, and now we can run the prover and we can prove that all of these transitions are correct. Now there's an obvious problem here, right? Which is that if you're cheating prover and you're running this system, right? You get sort of like to choose what is the external inputs you would feed to each of these things that the provers are proving. So you can feed them an inconsistent memory pattern, right? So you could have, for instance, a memory where you're saying to the CPU, yeah, you are writing to this address, this value here. And then a few steps later, you can say, oh yeah, and you're reading from this address, and by the way, it's this value here, which is a completely different value, right? And you will get out the wrong output from the computation. But none of the provers will know that something is wrong because their local view, everything looks great, right? I mean, you have some state of the CPU, you have some memory accesses that you're getting from the external, and you're doing the right transition, right? So the proofs will look great. And the problem is just that you're proving things that about the local transitions, but you're not proving that globally speaking, the memory is consistent. So that's a problem of memory checking, and people have come up with several different techniques to address that. So the high level of these ideas is we want to insert some memory protection for the CPU, right? So we still want to prove that the CPU transitions are correct and they're progressing correctly, but then we need to give them some protection that also the memory accesses they get to see are actually correct. So we can imagine augmenting the state of the CPU, ZI, with a digest of the memory, right? So think of this for now just as like a hash or a commitment to the memory. And then when we give the transition function these kind of memory addresses, then let's also give it some information so it can check that these accesses are correct. So let me give you, okay, so the big picture here then is, okay, so now with these additional checks, with these additional digests, when we do this incremental verifiable computation, now we also have memory protection, and now when we get out the correct proof for the result, we know that both the CPU has executed correctly and also all the memory accesses are consistent with one global random access memory. So let me give you an example of how this could be done. Okay, so think of a Merkle commitment to the memory. So we start by committing to the full memory in a Merkle tree, and we give the root as the digest as input, right? So part of the state. Okay, and that's just like small hash value, so it's a very small addition to the state. And now whenever you are accessing the memory, we will not only give the accesses to memory, but we will also give Merkle paths to the root, right? Now it's something you can, for every access to the memory, you can check that this is actually consistent with the memory that's committed in that Merkle tree root. Okay, and the cost as well, so sort of the logarithmic size of the memory, right, is sort of like the length of this path, right, and you have to check each of those, right, and that's sort of like, if it's a large memory and you're only doing a few memory accesses, then that's going to be cheaper than having constraints for the full memory. So this is great, it works. However, it's inefficient, right? Because for each access to the memory, the prover now has to prove that it's seen a Merkle path to the root of the tree. And proving hashes is expensive, right? So it costs a lot of constraints. So we implemented this with Poseidon, which is like a fairly ZK-friendly type of hash function, right? And we're talking about like hundreds of constraints that we have to implement and to check this path here. So the question is, can we do better? Okay, and the answer is going to be yes. So let me give you first a little bit of background as what it is that we really want to prove in order for the memory to be consistent. So here's a common technique that is often used, is to think of a read set and a write set that tracks all the memory accesses. Okay? And we will think of the execution as first we will do some initialization. That's just where we're writing what is the initial memory. In this case, I only have 2 addresses in here, right? Then we'll have the execution, okay? And when we do an execution, if we load a value, then we would read that value, and then we will write that value back again, okay? So for every access to the memory, we both do a read and a write. If we store a value, then we will read a value, and then we would write the new value that we're storing. And the reason we're doing this is that, well, every time we write something to a cell, then we update what is the timestamp when we accessed and what was like the last time this cell was used. So when we have a always read and then write pattern, we make sure that every cell has been written just once before that was the last time it was written to, and then we sort of like read that and then rewrite a new thing, right? So we're always making sure that the read set sort of like trails the write set. And then when we are done with the computation, then we'll just have the final read of everything and discard that. And the reason we do that is that we can actually now check that the memory consistent, it is equivalent to the constraint that the read set is equal to the write set. Okay, so you have some local checks, so you will check locally that, for instance, whenever you load a value, then you should be reading that value, but you have to write exactly the same value back, right? You cannot change the value. Whereas if you have a store operation, then you would read a value, but you can write something different back. So there are these kind of local constraints, okay? And then if those local constraints are satisfied, and we also have that the read set is equal to the write set at the end, then we know that the memory is consistent throughout. The question is now how to check that, right? Because these read sets and write sets, they also grow really big. Okay, so that's not something we want to store inside the zkVM. And for that, I'm going to talk about using multiset hash functions. Okay, so something that was proposed in the ZK context by Zed et al. In 2018. So a multiset hash function takes a set of values from a message space, okay, and produces a small digest, okay, and should have this compression functionality that that digest should be really small regardless of the size of the multiset. The other property we want is that if we have a couple of multiset hashes to 2 sets, we should be able to compute the multiset hash of their union. Okay, and remember these are multisets, so all the elements are counted with multiplicities. They may be repeating in the set. And finally, we should have collision resistance, that if we had 2 different multisets, then it should be hard to find them, so they actually map to the same thing. So let me give you a standard construction for that. So we're using here a group G. Okay, and think of this like a standard prime order group, which where the discrete logarithm problem should be hard. And then we take a hash function, And you may think of that as a random oracle for now. So, and then we just go through all the elements in the multiset, hash them, and we add together these hashes, right? Because hash outputs group elements. Okay? And it has the compression functionality, right? Because now, regardless of the size of the multiset hash is just one group element. It's also pretty easy to see that we have the incrementality property, right? So if you want to, if you have the multiset hash for one set, you have the multiset hash for the second set. When you add those two, right, then you're just taking the sum of all the hashes in both of the sets. You get the multiset hash of the union of those two sets. And finally, you have the collision resistance property, right? If you have two multiset hashes that are equal to each other, well, the first one is just the sum of hashes in that set. You can subtract then the hashes in the second set, and that should be 0. And if those two sets, well, if the two sets are identical, yes, obviously you get 0, right? But if they're different, then when you count with the multiplicities, so those are the A's, right, you would actually get a non-trivial sum to 0. And if you model the hash function as a random oracle, that means that now you have some group elements where you don't know the discrete logs and you have made them sum to 0, right? So now you've broken the discrete log problem. So how can we use a multiset hashing to check memory? Well, the idea is now that instead of directly keeping track of the read set and the write set, we will just have the digest of those. We will have the multiset hash of the read set and the write set and keep updating that. Okay? So on the right-hand side here, we have the digest of the read set and digest of the write set. The digest of the read set, well, we've not actually read any values, so that's just 0 to start with. The write set starts with the first initialization we do, and then we hash that, right? And then we keep on updating whenever we do one of these operations. We update those two sets accordingly. Okay? And at the very end, right, if the read set is equal to the write set, then those two digests, they match. And if the read set and write set is not equal to each other, then by the collision resistance property, the digests do not match. So that gives us a guarantee that the read sets and the write sets match in the end. And the cool thing is that this is like, you only keep track of the group elements, right, that these set hashes along the way and update those, okay? And even if you have different workers that are doing different slices of the computation, then that's still fine, right? It's just a local operation. I'm getting some digest and I'm updating that digest, regardless of what has happened elsewhere in the execution. So multiset hashing is a way to allow you to check that the memory is consistent just with local operations, and then this multiset hash digest that you're evolving over time. Okay, so how does that usually work? Well, you have the group. That could be an elliptic curve. Let's say it has a prime number of points for simplicity. We can generalize that. We have a cryptographic hash function that maps into the field, FQ, and then we typically have a map to group function that maps into the group, right? And then the hash to group function is the composition of those two. So that's the standard construction. And it's an expensive construction, right? Because what is the cost here? Well, you have to do this hash function first, and then you do sort of like a mapping, okay? And that hashing function is an expensive operation, right? This is a cryptographic hash function. So now you have to compute and verify a hash in every step. And this is where we're sort of like starting to think then, okay, what are the minimal requirements that we want from this hash function, hash to group function? We want it to have collision resistance, right? Because if you have two elements that hash to the same value, then it's very easy to find multisets with just singleton elements that hash to the same. But maybe we don't need cryptography for that. Maybe we can just use an injective map, right? That's that's like the idea we're exploring here. Okay, so can we just use that map to group function instead of having a hash? Okay, and of course this requires that the message space is of modest size, right? Because if it was arbitrary large elements, then, well, you do need a collision-resistant cryptographic function for that. But if it's a small size set, then maybe actually the size of the set is smaller than the group, and it's possible to have an injective function and get collision resistance through injectivity. And interestingly, when we do memory checking, then we do actually maybe have small sizes, right? So think about like what would in practice be the size of like you have an address, you have a value, you have a timestamp. Well, maybe there are 32 bits, 32 bits, 32 bits, or something like that. That's 96 bits, right? That is modest size. So we are actually in a situation where we could use just a hash function for modest size sets, for modest size elements, right? And therefore maybe injectivity is something that we can use when we're doing memory checking in zkVMs. So there's one other thing that we need to be careful now when we don't have like this hash function inside to make things look random. And that is, you may also be able to find two elements where we're mapping to the inverse of the element, right? Because in an elliptic curve group, it's very easy to just take the inverse of a point by flipping the y coordinate. So we actually need, and if you can find that right, then you can also find a non-empty set that maps to the same multiset hash as the empty set, right? Because M1 and M2 would, the multiset hash of those would just cancel out, right? And you would get 0. Okay, so we need to be careful about that. So we actually need a map to group function which is injective with respect to the x coordinates, right? So it's sort of like resistant to the sign flip. Okay? And interestingly, we can show that if we have those two properties, then we can actually get just use the map to group function, and it is secure in the elliptic curve generic group model. Okay, let me see. I have 2-3 minutes left. Yeah, okay. So I'll just very quickly give you sort of like a feel for what could this function look like, okay? So it's pretty straightforward. You take the message, you add a little tweak to it, and you try to use that as the x coordinate, right? And the tweak is there because only not all the x coordinates, only half of them are actually good x coordinates, so we need the tweak to just make sure that we get something which is a valid x coordinate. And then the function also needs to make sure that we cannot flip the sign. We suggest if q is equal to 3 mod 4, that we just make sure that y is the quadratic residue, right? Because only one of y or minus y is going to be a quadratic residue. And you return that point. Okay, and let me, okay. And, okay, so what are the constraints we need to ensure this? Well, we need to make sure that x is actually something that matches a point in the group, right? We need to make sure that x is a valid jump with this tweak. We need to make sure that the y coordinate is unique, so we cannot flip the sign. Okay, and all of those are pretty simple constraints to verify. Okay, so using this kind of multiset hash to map to group function, then we have a deterministic map that can be used to sample such points. Okay, there's one more thing to be a little careful about, which is that you could imagine that the prover, instead of using the smallest tweak, used a different tweak. And this is why I'm switching from map to group functions to map to group languages, because actually it turns out that it doesn't help the provers if they're cheating that way. And that means that we don't have to go through the trouble of proving that the tweak is the smallest possible one, right? It just has to be one of the valid tweaks. Okay, so the construction, if we instead use the map to group function, looks like this, just as before. And as you've seen, we only need a very small number of constraints to check that a map to group function is evaluated correctly. Okay, and with that, I'll stop my talk. Thank you.